In this video, we're going to show you how you can tune the hyperparameters of your machine learning model in Python using the scikit-learn package. If you're new here, my name is Tinin Nanta Sanamat, and I'm an associate professor of bioinformatics. On the DataProfessor YouTube channel, we cover about data science concepts and practical tutorials. So if you're into this kind of content, please consider subscribing. So before we begin, let's talk briefly about the concepts of hyperparameters. So hyperparameters are parameters that can be adjusted and fine-tuned in order to improve the performance of the machine learning model. So let's take, for example, the random forest algorithm. There are several parameters that we can potentially adjust. And the two major parameters that are widely adjusted are the n estimator in scikit-learn. It's called n-tree in caret, our package. And max features in scikit-learn is called mtry in the caret r package. So in this video, we're going to focus on these two hyperparameters of the random forest algorithm. So without further ado, let's get started. So the first thing that you want to do now is to head over to the DataProfessor GitHub and then click on the code repository. Find the Python repository and click on that. Okay, click on the hyperparameter_tuning.ipynb and then find the raw link and right click, save link as, and then save it to a desired folder in your computer. Okay, so I'm going to minimize this and open up my Jupyter notebook on my computer. Open up my command prompt, going to the folder. Okay, Jupyter notebook. Oh, I have to activate my Conda environment. And then open up Jupyter notebook. Okay, and then open up the hyperparameter tuning.ipynb. So let's begin, shall we? So we're going to take some of the codes from the previous tutorial and we're going to generate the synthetic data set. So here we're going to use the make classification function of the scikit-learn.dataset module. And then we're going to assign the x and y variables where the generated data set will be assigned to these two variables. And in here as argument, we set the number of samples to be 200 and the number of classes to be 2, the number of features to be 10, number of redundant features to be 0, and then we set the random state to be 1. Okay, so go ahead and run this on my local computer. I'll just hit on the shift enter. Okay, and then let's have a look at the generated data set. So here we have 200 rows and 10 columns, which corresponds to 200 data samples and 10 features. And for the y variable, it is 200 rows and 1 column. So that is the class label. And the class label is comprised of 2 classes. So if you would like to have a look, you can hit on X and then enter. Shift enter, and then you're going to see the data set here, but it might not look that intuitive. So let's import pandas, and then you can generate a data frame and put X inside. Right, so your input features or the X variable will look like this. So there is 10 columns and there are 200 rows. So why we're seeing 199 here is because the first row is called the ID of 0. So Python starts with 0 as the first number. So here at the bottom, it says that there are 200 rows and 10 columns. So we could do the same for the Y variable. Okay. We could assign it to X and then a Y. Run it, and then we can even have a look at X, add another cell, have a look at Y. Okay, so Y has 200 rows and 1 column, which is the class label. And because there are 2 classes, it can be either a 1 or a 0. So the next step is we're going to split the data using the 80-20 ratio. So 80% will go to the training set and the 20% will go to the testing set. And so here we're going to use the train test split function of the scikit-learn.model selection module. And then 4 variables will be generated: x train, x test, y train, y test. So the pair of x train and y train will be used to build the model, and the x test will be used to evaluate the model that we have built on this external or testing set. And then we will then compare the predicted class label with the y test. So that will allow us to derive the accuracy score. And this splitting will be performed by the train test split function. And as input argument, we're going to use the x and y variables, which we have generated previously. And we set the test size to 0.2 because we want the testing set to have 20% of the data. Okay, so the next step is to examine the data dimension. And we're going to also use the dot shape to do that. So x train shape has... Okay, so we have to run this first. So xtrain.shape has 160 rows and 10 columns. And let's run the next one. Testing set has 40 rows and 10 columns. So 160 corresponds to 80% and 40 corresponds to 20%. So before we even start to tune the hyperparameters, let's start with the basic of building a simple machine learning model using random forest. And we're going to assign some default values to the 2 hyperparameters that we're going to optimize later on. So firstly, we want to import the necessary libraries. And so we're going to import the random forest classifier and the accuracy score. And so both are coming from the scikit-learn package and coming from the ensemble and metrics module. And now we're going to assign to rf variable the random forest classifier, and as default values we're going to set the max features to be 5 and the number of estimators to be 100. And so now we're going to apply the rf classifier to construct a training model. And we're going to do that by using the rf.fit function. So notice that rf here is the same name as the rf variable. So let's say that if you change this to be model, then you're going to have to change this to be model.fit. Okay, so let's change that back to rf. Oh, okay. I think it's because we use the data frame and it's expecting a one-dimensional array. Okay, so let me generate the data set again, and we're not going to define x. Okay, we're just going to show it. So let me generate the dataset again. So the previous error, it tells us that it expects a one-dimensional array, but then because we use the pandas data frame, it is a two-dimensional array. So let me generate the dataset once again. Okay, and then we're just going to show you the x as a data frame, but we're not going to save it into the x data frame. Okay, so you're just going to see it, what it's look like, the structure of it in 2 dimension. Okay, so the data splitting occurred as expected, as previously explained, where 160 goes to the training set and 40 goes to the testing set. And so now we're going to build a simple machine learning model. So let's run this again. Okay, and then we're going to construct the training model once more. Okay, so no error was obtained because it receives the expected one-dimensional array. By one-dimensional array, what do I mean? It's like this. But if we make it into a data frame, it will look like this, like the one above. Right? So this is 1 dimension, this is 2 dimension. So the first row here is right here in the bracket, right? Minus 1.511 right here, minus 1.511. The last value is minus 0.87, minus 0.87. And so the second row is right here. And so the first value is 1.55. Right here, 1.44. The last value on column 10 here is minus 2.62, and right here is minus 2.62. So this is 1 dimension, this is 2 dimension, okay? So let me cut this out, and let's continue. Now we have constructed our prediction model, and let's evaluate the score. So here we have two options. We have two methods for you to try, and let's see which one you like. So the first method is we're going to simply use rf.score to obtain the accuracy score of the prediction model that we have generated in predicting the data samples of the X-test variable. And so that is the 20% subset that we have previously split at the beginning of this tutorial. So here we got a 0.825 accuracy score. And so this is very simple. It takes in the argument X test and the Y test. And the second approach that we're going to try is going to take you two more code cell. Okay, so the first step is we're going to first define a variable called Y prediction, YPred, and then we're going to use the rf.predict function. And as input argument, we're going to use only the X test. Okay, so this is the unlabeled data. Okay, and so once we get the prediction, and so the prediction will look like here below. So YPred will be the first array here, and the Y test will be the second array here. So the YPred will be the predicted value of the Y, and the Y test will be the actual value. So now we're going to use the accuracy score function to evaluate the accuracy score using as input argument the Y predicted value and the actual Y value. Okay, so when we run both of them, it gives you the same result. Okay, so it's 0.8. So 0.825 was probably from a previous run that I have done previously before I uploaded the Jupyter Notebook file. So 0.8 is the current dataset that we have just generated. So owing to the dynamic of the dataset generation, you might get different results from what I'm getting right here. But the RF score approach and the accuracy score approach here will give you the same value. Okay, so now we're going to start with the hyperparameter tuning. And the two hyperparameters that we're going to use are the max features and the n estimators. So max features represent the number of features that we will use to construct the prediction model, and n estimators is the number of trees that we're going to use to construct the prediction model. And the grid search CV function will be used to perform a exhaustive search of the optimal parameters in a gridwise manner, meaning that it will perform all possible pairwise computation of the two hyperparameters that we're going to use in the examples here. So let's say that if max features, we use a total of 5 different values, and the number of estimator, we use a total of 5 different values. So it is a 5 by 5. So it's going to perform the computation for 25 times, right? Because 5 times 5 is equal to 25. So let's look at the code here. So the first one is to import the grid search CV function coming from the scikit-learn.model selection module. And we're going to also use the numpy as well. So numpy will be used to generate this range of maximal features and also the range of the n estimators. So let's have a look. When I import numpy as np, and then I typed in np.arange and 1,6,1, enter. So I get 1, 2, 3, 4, 5. So notice that the number of 6 is not included here. So what you will need to do is you will need to add an additional 1 to it. So if you want 5, then you would add 1. So you would have to put 6 here. If you would like to have 10, then you would have 10 plus 1. And so you would put 11 here. Okay. If I want 1 through 100, it would be 101 here. Okay, and it shows 1 through 100. Okay, so now we know that we will use a range of 1 to 5 here. And let's have a look what does this do. So this is the number of trees that we're going to use. So it's going to start with 10 trees, and it's going to incrementally increase by 10 trees because that is the step size or the interval size, and it's going to stop at 200, right? So the minimum value here is 10 and the maximum value is 200. So in other words, you could say that 10 is the start and 200 is the end. So you would take 210 minus 10 and you would get 200, which is your real n. Okay, so let me cut this out and then let's look at it again. So these two parameters will be used as input for the param grid. And we're going to use the dictionary function. And then the max features will be equal to the max feature range. And the n estimator will be equal to the n estimator range. So this will provide the grid that the subsequent lines of code will be using. Okay, now we're going to define rf variable to be the random forest classifier. And then the grid will be equal to the grid search CV function. And then the estimator will be using the rf variable. And the param grid will be using the param grid variable. And the param grid variable will be using the max feature range and the n estimator range as the input argument. And then we're going to use 5-fold for the CV, right? Because it is grid search CV. It's going to do this in a cross-validated manner. So in a nutshell, in an n-fold cross-validation, we're going to leave out one fold, and then we're going to use the remaining fold to construct the prediction model. And then we're going to evaluate that prediction model on the left out fold. And then we're going to do this iteratively until all of the fold have been left out one time. And then the prediction result from 5 of these iteration will be averaged. Okay, so let's have a look at the next grid. So the next one will then perform the actual model building, and we're going to just shift enter. Okay, so we have to define it first. So hit on the previous cell and shift enter. So notice that this will only define the variables, right? So it's kind of like preparing the food materials, but you haven't yet cooked the food. So it's kind of like chopping all the vegetables, marinating all the meat, and then the actual cooking will be the model building process that we're going to do right here. So grid.fit is the actual cooking, actually turning on the oven or turning on the fryer. Okay, so shift enter on this grid.fit. So it takes a couple of moments to construct the models, because here it's going to build several models in a grid-wise manner. So as we have previously explained, if we have 5 features and then we have a total of, I think it's 2, the stop size is 200. So here we're using max features of 1 through 5, and we're using the number of estimators from 10 to 200. So the dimension will be about 5 by 20. And so in a 5 by 20, if you multiply 5 by 20, you get 100. So it's going to build you 100 prediction model. Okay, so now, these are the previous results. All right, so I think the model has already been built. Let's look at the results. So the best parameters are having a max features of 2 and n estimators of 30. And the score is 0.9. Okay. And so we're going to extract only the max features and the n estimators along with the accuracy score from the results of the grid search. So the data frame will look like this. There are 100 rows and 3 columns correspond to max feature, n estimator, and accuracy score. And so we're going to use these results as the basis for constructing the subsequent plots of the 2D contour plot and the 3D surface plot. So they will be the result of our grid search. So before we can actually build the contour and the surface plot, we need to prepare the data. We're going to have to reshape the data a little bit. So now we're going to group the data according to the max features and the n estimators. So we're grouping them, we're sorting them. So we see that the max feature will start from 1, 2, 3, 4, 5. And then within max features, the n estimator will start from 10 until 200. And so it will be 10, 20, 30 until 200. So it's going to order the data in this block of code. And then subsequently, we're going to have to pivot the data, right? So the max features will constitute the rows that we see here. However, the n estimators, it is right here as rows. It will have to be pivoted into the columns. So now we have a 2-dimensional column. So we have a 5 by 20 column now. Before, it is only a 100 row by 1, because group by function will not count the 2 features that we're grouping it by. So only the accuracy was counted as the column. Okay, so here, the first column here, max features, will be the first column here and the pivoted data. And the n estimator will be pivoted, meaning it will be like this, kind of like moving the data horizontally from vertical to horizontal, from rows to columns. Okay, so each of this value will be the columns here now. And then the values will then be also pivoted and will populate the newly pivoted data frame. And so now we're going to extract these values and then assign it to the x, y, z variables. Run it first. Oh, okay. Did I not run this? No, I did not. Okay, so let me run this. Okay, now we have already assigned it to x, y, z. Let's have a look. X, y, and z. Okay. So now the fun part comes to make the 2D contour plot. So this will allow us to visualize the landscape of the two hyperparameters of the random forest model. And so let's go ahead and run this. No module name Plotly. Oh, okay, so I have to first install Plotly. Install Plotly. Let's head over back to Jupyter Notebook. Okay, so let's run the code again. We shift entering this one. Build a simple machine learning model. So you see that the second iteration that we're doing this, the prediction score changes. Okay, the model building. So this will take a couple of seconds or 1 minute. Okay, so the model is built. Let's head over and run the other ones. So now the max features is 3 and the n estimators is 140 and the maximal accuracy score here is 0.9. So these two parameters will give you the maximal accuracy score. So that is the purpose of the grid search parameter, is to find the hyperparameter that gives you the maximal performance for your prediction model. Let's go ahead and run the subsequent data frames here. And then we're going to prepare the data for our contour plot and surface plot, pivot the data, assigning it to the x, y, z variables. So let me mention again the x variable, the y, and the z. So let's run the 2D contour plot. Okay, and estimator, okay, this looks correct. So the max features has the range of 1 through 5, and the n estimator is from 10 to 200. Okay, so this is the contour plot. And so the yellow color represents the region that provide the maximal performance, and the purple regions are the ones that provide the worst performance. So here we can see that the lower left region provided the worst performance. So it means that there are few features used to create the model and low number of trees to construct the model. And as previously shown above, the maximal region is maximal feature of 3 and n estimator of 140. So 140 is right here, and number of 3 is right here. Right, so it's somewhere here, which gives you 0.9. Actually, this one is, okay, I think it's somewhere here, right here, in the yellow region. Right, the other one are almost 0.9. They're like 0.89375. Okay, so right here, x of 140, y of 3, and z of 0.9. So the accuracy is right here. So this 2D contour plot is interactive, and you can play around with this. So now let's head over and create the surface plot. See if the labels are correct. Max features is 1 to 5, and estimator is, okay, up to 200. Okay, that's correct. So this is the 3D version. You can zoom in if you like. You can even adjust this to be a bigger one. You could make it like 1,000 by 1,000. Right here. Okay, so now it's 1,000 by 1,000. So this is the 3D landscape, the surface plot of the hyperparameters. So as previously mentioned, when we have few maximal features and few n estimator, the performance is detrimental. And so we see that when the n estimator is about 140 and the max feature is about 3, it gives us a peak. Okay, the peak is right here, right here, right here. It even highlights the path. Okay, that's good. Can we see the peak? I think there are other regions that have similar level, right? Like 180 and 3 max feature give you the same peak. But this will take more time because it requires 180 trees, whereas this one requires only 140, right? Is it the highest one? How about this peak? 0.89375. How about this peak? 89375, 89375, 89375, 89375. Okay, so this is the 3D contour plot, the 3D surface plot, right? Some people call it the 3D contour plot as well. And so as always, learning data science require building your own portfolio. So please practice this on your own data set and let me know in the comments down below what interesting data that you are working on. Thank you for watching. Please like, subscribe, and share, and I'll see you in the next one. But in the meantime, please check out these videos.